Hello, everyone. Welcome. It is my pleasure to introduce Dr. Britt Raubenheimer from the Woods Hole Institute of Oceanography. She's going to be speaking today on some nearshore processes. Britt did her bachelor's degree in physics from Middlebury College in Vermont. She then spent some time working with the USGS in St. Petersburg, Florida, and where she was sort of introduced to the world of coastal processes. She then moved on and went to Scripps Institute of Oceanography for her PhD. Some of her research interests include surf and swash zone hydrodynamics, interaction between ocean waves and the coastal groundwater, and morphological evolution of these tidal flats and inlets. And more recently, she's been doing a lot of work sort of tying large-scale storms to changes in the coast. And she's going to be talking about some of the techniques she used for that ongoing work today. Britt?
Thank you, Josh, and thank you everybody for coming here today, and thank you, Josh and Lynette, for inviting me. One quick comment before I get started. If anybody has a question during this, raising your hand is not going to do any good whatsoever. So if you have a question, don't hesitate to speak loudly and interrupt me and ask the question. But don't get frustrated keeping your hand up in the air. So as Josh said, I'm going to talk a little bit about some observations that we made about waves, wave-driven setup, which is an increase in the mean water level owing to breaking waves, and in swash, which is the waves running up and down the beach, and also dune erosion simultaneously during major storms. And I'm going to be using a technique known as Lidar, which stands for light detection and ranging, and I'll talk a little bit about the Lidar technique that we're using. And this photograph here shows the types of conditions that we're trying to make measurements during. This photo was taken during Hurricane Matthew, standing on the dune near Duck, North Carolina, looking offshore. This is an Army Corps research facility where Josh has done a lot of work. And you can see their pier on the upper right-hand part of the image there. And that pier extends out to about 8 meters water depth. You can see that the foam and all the white water from the breaking waves extends way out past the pier. So these are about 5-meter waves offshore. They're pretty big waves. They're breaking well offshore the pier and coming in through the surf zone. And during these types of conditions, depending upon the tide level and the storm surge level, those waves can end up coming all the way to shore and then slamming into the dune, as shown in the lower photograph. When they do that, they tend to cause a lot of erosion of the dune. If they get up high enough, they might overtop the dune and cause flooding. As you can imagine, the people that own the houses up north of the property don't really like it when their dune's disappearing. Sometimes every winter, a house or two falls into the water. They spend a lot of money trying to replenish that dune and bring sand onto the beach to protect their homes, but the erosion can be more than they can really balance against. Now, as you can imagine, there are quite a few parameterizations for how this process occurs because people are very interested. A very common parameterization is that the change of volume in the dunes, so the dune erosion, is proportional to the difference between the 2% run-up, which I'll explain more in a minute, and the elevation of the dune toe. So the 2% run-up is the elevation at which only 2% of the waves of the water is exceeding. So basically what that's saying is that the dune erodes when the water gets higher than the dune base. Not too terribly surprising. But the dune toe elevation, that's something we can define pretty easily. The 2% run-up gets a little bit more complicated. And it depends upon several parameters. It depends upon the tide. When the tide's higher, the water level's higher. When the storm surge is higher, the water level's higher. But then there are also some terms that are the wave-driven part, and that's what we struggle with more. Those terms circled in red. The first term is the mean run-up. That's the increase in the water levels owing to the breaking wave, otherwise known as the setup. So the breaking waves come into shore. As the waves get closer to shore, they might get sort of peaky, they pitch forward, they eventually turn over, they slam into the water surface, and they put a stress on the water surface. It's similar in many ways to the stress on the water surface from a wind. If you think about a wind blowing across a lake, the wind can pile up water on the downwind shore of the lake. Similarly, if you sit in a bathtub, you can use your hand and pile up water on the side of the bathtub. The breaking waves act very similarly. They put this stress on the water surface that piles up water, and the setup is largest right at the shore. So you get an increase in water levels that's particularly strong near the shoreline. The last two terms in there are the swash. This is the fluctuation of the water level about that mean run-up. And we tend to break that into two different parts that describe two pretty different processes. So there's the sea swell swash. The sea and swell are the things your eye sees. Those are those 5-meter high waves that are generated by the wind during a storm. And as those waves come to shore, as I mentioned before, they tend to break. When they break, they dissipate. So they lose energy as they come across the surf zone, and they keep on losing energy, but there's still some energy at the shoreline. That wave runs up and down the beach. That's a sea swell swash. The infragravity swash, the infragravity waves are actually generated by the sea swell waves. So they tend to have fairly small amplitudes offshore, but they have very long wavelengths. So they never get very steep. They never pitch forward and break over. Instead, they do what we call shoal. Same sort of thing as a tsunami. Tsunami amplitudes are small offshore. They get larger as you come into shallow water. That's because they don't break, they don't dissipate, they conserve energy flux. And as you squish all that energy into shallower and shallower water to conserve the energy, the amplitudes increase. So differences here, the sea swell waves are big offshore generated by the wave. They dissipate coming across. They're small at the shoreline, but there's still energy. Whereas the infragravity waves are small offshore, they don't dissipate, and are largest at the shoreline. And if you've gone to the beach during moderate wave conditions, you've probably experienced both of these. You look offshore, you see these nice waves. They might be curling over. They're the waves that surfers want to ride on. But if you stand at the edge of the shoreline for a little while and you think, okay, this is about as far as I can go and put my towel down and stay dry, if you stand there for a minute or two, all of a sudden a couple big waves might come up higher up on the beach and get your feet wet. Those are the infragravity waves that have 1 to 2 minute periods, and your eyes don't really see them, but your feet might notice them. So we want to understand these processes, these wave-driven processes in particular, better, especially during storms, but it's not so easy to make measurements during storms. We call this the washing machine. It's all foamy white water. There's big waves. The waves in the photo are breaking over the end of the pier. That pier is about 25 feet above the water surface. Those waves are getting way up high, splashing across the top of the pier. They're smashing down. When they come down on your instruments tend to break. They're also picking up a lot of sand, so your instruments are getting sandblasted. If you put instruments up on a dry beach on shore, the wind's howling, it's also sandblasting your instruments. There's rain, there's salt spray. If you put out a camera, the lens tends to get all slimy and foul. So we're trying to develop a new technique known as Lidar, which, as I mentioned, stands for light detection and ranging. And it works by sending out a beam of light. The beam of light reflects off something, in our case, the beach or the water surface, goes back to the instrument. It measures its travel time back and forth. From the travel time and speed of light, it can figure out the distance, and it knows what angle it transmitted that beam of light at, so it can figure out where the reflector was. And it operates in 2 modes. It can send a beam of light, it rotates around and can send a beam of light out, back and forth, so it's getting points going across the beach, say, from the dune out to deeper water. And it also will rotate, so it can make a 360-degree topography map. The image down below is just a comparison of the LiDAR and the GPS. The LiDAR is shown in red here, the GPS measurements in black. This is from a laboratory experiment. Vertical axis is elevation, horizontal axis is distance cross shore. So on the left-hand side, you're at the top of the beach, going offshore to the right. And the bottom line is you can't see the difference between the LiDAR and the GPS signal there. That's because the vertical range is about 10 meters, and the difference, the root mean square difference between them is on the order of a centimeter. So it's really in the noise. I've actually shown a difference plot at the bottom. That vertical range is plus minus 10 centimeters. That red curve is a difference between the GPS and the LiDAR. And you can see a few wiggles in there, so there are some differences. We don't actually know which one's right. The LiDAR is making very dense measurements. GPS, I don't know if you've ever gone with Tom when he's pushing his dolly with the GPS. You're running across ripples. You're not getting every little point out of there. So we don't actually know which one of those is right, but they're both very similar. We've used LiDAR to map the dune during some big events. Some examples are shown here. These are both during Hurricane Matthew, I think. On the left, what you see is an aerial view of the beach and the dune. And then the color contours on top of that are the difference in sand level from after the storm to before the storm. So the hot pinks are where the dune eroded or the beach eroded on the order of 4 meters. If you look at that hotspot, the panel on the right just shows what the dune profile looked like during the peak of that storm. So on the right-hand side, the vertical axis is elevation, horizontal axis is distance offshore. The blue curve is the profile at the beginning of the storm. So if you look at that blue curve on the left-hand side, you're on the crest of the dune. If you move over to the right, you're going across the crest, down the front slope of the dune, and then out onto the beach. The color curves are the profile every hour during the peak of the storm. And what you see is that that dune eroded about 3 meters vertically and about 3 meters horizontally over about 6 hours. So 3 meters by 3 meters, that's more or less the size of a regular office. So if you go into Josh's or Tom's or Diane's office and look around, that office disappeared in 6 hours. And it's also about the size of the width of somebody's porch. So if their house is right in the crest of the dune, they probably lost their porch. So a lot of sand moving around pretty rapidly. Well, we also wanted to make sure that the LiDAR would measure the hydrodynamics, the mean run-up and the waves during the event. So we did a study, put a LiDAR up on the dune, shown in the photograph here. So it was looking offshore. The figure here shows the beach profiles from that LiDAR, the vertical axis elevation, horizontal axis distance offshore, just like in that prior plot. The blue curve is at the beginning of the study. The red curve is at the end of the study, about 10 days later. And the other color curves are the profiles each day in between. So this beach basically eroded a little bit and then it accreted back to its original state. The black circles are pressure gauges that we deployed in the beach. Pressure gauges are a standard way to measure the mean run-up, the setup, the wave heights. So this is ground truth, basically, for the LiDAR. Notice that some of those pressure gauges are offshore of the color curves. That's because the LiDAR can only measure the beach profile, the sand levels, when the beach is dry. When the beach is underwater, it's measuring the water levels. So a couple of those pressure gauges were always underwater, and we don't actually know what the beach profile was like above them. One of the things, first thing we're interested in is the total water level. That's what I've shown here. The vertical axis is the LiDAR observations. Horizontal axis is the pressure measurements. The diagonal line is a 1-to-1 line, so that's perfect agreement. The colors are for the different pressure gauges. So the red pressure gauges were further offshore. The blue pressure gauges were closer to the LiDAR, right near shore. And notice that all those points fall pretty well along that 1-to-1 line. Root mean square differences between these two techniques are on the order of a few centimeters. Also notice there's no real difference in the amount of scatter or error difference between the differences for the red or the blue. So there's no loss of accuracy of the LiDAR as it gets farther away at longer distances, longer ranges. One thing we're interested in, as I mentioned, is the setup. That's the mean water level increase owing to the breaking waves. That's what's shown here. Again, vertical axis is LiDAR, horizontal axis is the pressure, black diagonal is the 1-to-1 perfect agreement line. You see a little bit more scatter here. That's mostly because the range is smaller. This is only about a 2 meter on either side or less than that. So, but basically, again, the root mean square differences between the two techniques are on the order of a few centimeters. In this case, you do notice that the red symbols are all at the lower edge, low values, blue symbols at larger values. That's just because the setup increases as you come closer to shore and those blue pressure gauges are farther up the beach. So they're measuring more wave-driven setup on the order of a meter when you get right up to the beach. There can be a fair amount of setup. So we also care about the wave heights. That was another term in those equations. This is the infragravity wave heights shown here. Verticals LiDAR, horizontals pressure, and similarly the root mean square differences between the two techniques are on the order of a few centimeters. If I go to the sea swell wave heights, you see a little bit more scatter there. And in particular, if you look at just one color, you see trends sometimes. The slope is not the same as the 1-to-1 slope. And I can overlay a line there for the orange points. That line actually is showing, I say tide on it because when the tide is higher, the water is deeper, so the wave heights can be bigger. So really the points that are further up that line are at higher tide, the points near the bottom of the line are at lower tide. So there seems to be a tidal trend in the differences between the LiDAR and the pressure. That trend is there throughout the experiment, and it actually happens in almost all the instruments to some extent or another. We don't know yet what's causing that. And that's something that's there's still some ongoing work looking at these comparisons. But overall, again, the difference between the two techniques is on the order of a few centimeters. So in this case, we're looking at things during a storm where these signals are on the order of a meter or two. We're not going to worry about a few centimeters. So in summary for this evaluation of the hydrodynamics, the Lidar and pressure estimated setup and wave heights are similar, few centimeter type differences. So we're going to use the Lidar. We think we can use the Lidar to look at simultaneously the dune erosion and the hydrodynamics during storm events. There is some ongoing work with the Lidar technique, as I mentioned, trying to figure out this tidal dependence of the differences with the pressure for the sea swell waves. Also, we have some questions about exactly what the Lidar is seeing. Is it reflecting off the foam when the water's really foamy? Is it reflecting off the water? Does it penetrate the water? Some of that might actually be Lidar instrument specific. Actually, when Steve and I got our Lidar, which was, a little bit more than 10 years ago, we had written a proposal. We'd gotten a cost estimate for the Lidar. We got it funded. We went to the company and said, oh, great, we want exactly that Lidar that we got the cost estimate for. And they said, oh, great, wonderful. We're happy to give you that Lidar. Turned out it was this ancient dinosaur Lidar. It was the last one on the shelf. They had made newer, better models that rotated faster, got higher sample rates. We didn't know that. We bought the old clunky one. But it turns out our Lidar has a 900 nanometer wavelength, which reflects off water better than the newer models, which are 1500 nanometer wavelength. The drawback is that our Lidar is not eye safe, so you have to wear goggles, or if you're blind, it really doesn't matter anyway, so you just use the Lidar. So that might be instrument specific, and actually if we can figure out if it's reflecting off the water or the foam, that might help us learn something about these breaking waves and the rollers, how much foam is on top, and comparing with the pressure gauge might help with that as well. So figuring that out actually might give us more information for these studies.
Britt, question? What about rain and sea spray?
So they do get reflections off some of the sea spray. We have them in a case, so it's not getting, it can be out in the rain. Some of the newer models, you can actually get cases with windshield wipers, but we had, as long as you clean the lens once a day, once every other day, we haven't had any real problems with them. There is some post-processing, cleaning up reflections off of spray, spray up into the water above the waves, especially when the waves are breaking as much as the rain. Also reflections off of birds and people, but there aren't too many people on the beach during the middle of the storm. Other questions? Okay, so we did decide to use these Lidars to look at processes during storms. These are some photographs of the Lidars we used. The photograph on the bottom left is of the Lidar on the pier that we shined back towards a dune. We're doing topography with that, having it rotate and sweep through to look at those changes, the color contours of the dune erosion during the storm. That photograph was actually taken in the middle of Hurricane Matthew. The hurricane came through, it had about 90-mile-an-hour winds. That created havoc with the power system on the Outer Banks. We did have a generator for backup power. So we switched over to the generator, but that caused problems with the Lidar. So we had to go out into the pier to fix the Lidar, get it going again. I left Hugger back in the office, 90-mile-an-hour winds. I was afraid she'd get blown off the pier. It was pretty wild out there, actually. But we got the Lidar going again and got measurements of the dune erosion. So that Lidar is looking at the dune shown in the middle photograph and mapping out its change and its erosion during the storm. We also have a Lidar on top of the dune, and that Lidar is looking offshore and measuring the beach profile and also the hydrodynamics. So it's sweeping back and forth across that line that I overlaid right there. We also, during Matthew, put up a second Lidar that was closer to the pier near the south end of the dune. It was on the jack-up tower. That jack-up tower was rated for winds up to 120 miles an hour, so great, no problem during Matthew, except that power issue also took out that Lidar. Well, the jacket tower is rated for 120-mile-an-hour winds, but they said you should not lower it or raise it or move it at all if the winds were over 60. So we scratched our head and said, do we chance it? We decided we should. So we got a team of about 6 of us with guy wires. We took the tower down. We were able to fix the Lidar, put it back up, and the tower didn't break, so we were really happy. So we got measurements with that one during the storm as well. So this is some of the dune erosion that we observed. The upper panel there is an aerial view of the beach. Looking down, you can see the pier sort of on the left-hand side of the image. North is to the right, going along the beach. The ocean's to the bottom. And the color bars that I've overlaid on there is where the dune erosion was maximum during each of these storms. Down below are actually the Lidar measurements of the dune erosion from after the storm to before the storm. So the upper small panel is for Hurricane Joaquin in 2015. When it came by, there was about 8 meters of erosion at the most eroded location of the dune. And that location is shown by the pink arrow. It's where the color contours are hot pink, 8-meter change in the dune. So that was a pretty big change in the dune there. During Hurricane Matthew, down below in green, there was about 3 meters of erosion at the location, again pointed to by the pink arrow, and that corresponds to the green bar in the upper panel. During Hurricane Jose, when it came by in 2017, there was no dune erosion, but just after that, during Hurricane Maria, the dune eroded about 1 meter just south of the pier. So each one of these locations has moved sort of further south along the dune, and one of our questions is, why did one section of the dune erode while another section remained there? If you have a house, you might really care about that because your neighbor's house disappeared, but yours was okay, hopefully, or vice versa. So trying to understand why one part of the dune's eroding and other parts aren't is something it's definitely one of the prime topics that we're looking at. Well, if I go back to that parameterization for what the dune erosion is related to, the change of volume is the difference between a 2% run-up and a dune toe elevation. So the first thought, and several other studies have suggested, that the dune toe elevation before the beginning of the storm is really important to where the dune erodes. In this case, though, the dune toe elevation was completely uncorrelated with where the maximum erosion occurred. So the dune toe elevation wasn't the answer to why one section eroded rather than another. So looking further at that 2% run-up, the parameterization suggests it might depend upon the offshore wave conditions, the wave height or the wave length. So the next thing we looked at, also the storm surge, that's what's shown here. Wave heights are in red, storm surge is in blue. The panel on the upper left is for Hurricane Joaquin. If you look at Hurricane Joaquin in 2015, the maximum wave heights were about 5 meters. The maximum storm surge was about 1 meter. Matthew in the upper right, maximum wave heights were about 5 meters. Maximum storm surge was about 1 meter. Hurricane Jose and Maria occurred in 2017, right after each other in the bottom. Again, for both of them, maximum wave heights about 5 meters, maximum storm surge about 1 meter. So this offshore wave conditions look to be pretty similar. The offshore storm surge was pretty similar for all these storms. So looking further at that equation, breaking it down further, the 2% run-up also depends upon some sand level conditions, both what we call the foreshore slope, which is right up where the Swash is, on a part of the beach that is alternately wet and dry, and also the elevation of the sandbar, which is a pile of sand that's off in the surf zone where the waves are breaking. Both of those have been suggested to affect the 2% run-up. So these panels are showing now surveys of the sand levels following each storm. So this is the first survey we could get at the end of the storm. In each one of these panels now, the vertical axis is cross-shore distance. So the ocean's to the bottom of the panel, the dune is to the top. The bright red colors are the top of the beach right at the base of the dune toe. So they're about 3 meters elevation. The dark blue is deep in the water. The horizontal axis is alongshore distance, so north is to the right, keeping the same contours. So if you look at the upper left panel, that's for Hurricane Joaquin. There's also a blue bar at the top that shows where the maximum dune erosion occurred. But looking at the Hurricane Joaquin panel, starting at the top, you're in the red, you're right at the toe of the dune. If you move down that panel, you get into a yellow area, that's basically mean sea level. Going further down, there's that blue-green color that's underwater a little bit. There's also some dark blue holes you see in there, big patches of dark blue. Those are big holes basically in the bathymetry. If you went through one of those holes, you'd go down deep into the hole, and then you come back up into that blue cyan color. So that's the sandbar, where you come back up onto that higher sand before you dip back down towards the offshore. So during Joaquin, there are some of these big blue holes, and actually the erosion, maximum erosion occurred onshore of one of those holes. If you look to the right during Hurricane Matthew, there was a much more wide, diffuse blue-green color, not so many deep holes, although the maximum erosion occurred sort of near where that hole is on the left-hand side. That's actually the trough right near the pier. During Hurricanes Jose and Maria at the bottom, there's a combination of sandbars and holes, and the erosion occurred again near that hole underneath the pier. That hole's gotten larger and bigger before that storm, and it's much more pronounced. And also notice that the yellow, green, red area is much wider. The beach slope was more gentle up on the beach. So differences, quite a big differences in sort of what these sand levels look like during each of the storms. So we think that maybe those sand levels are related to why there's this alongshore variation in erosion. But how is that, how are they related was still unclear. So now what I'm going to do is I want to look at the hydrodynamics as well as the beach profile. I've now overlaid the location where the Lidar was during each of these experiments by the black dashed line highlighted in white. It was to the north during Hurricane Joaquin and also during Jose and Maria, and close to the pier. I'm going to use that closer to the pier Lidar during Hurricane Matthew. And the Lidar only looks at the hydrodynamics in the beach up near where the red-yellow area is, where the beach gets alternately covered and uncovered. The other area offshore, we're just going to look at what the beach profile looks like because that might be affecting the hydrodynamics that we observe. So I'm now going to show you profiles from the top of the dune or the base of the dune out to deep water along each of those lines. So that's what's shown here. The vertical axis is elevation, horizontal axis is distance offshore. The different color curves are the profile for different storms. The blue is for Hurricane Joaquin, green is for Matthew, pink is for Jose and Maria. If you look at the blue curve and start at the top, again, going to the right, you go down from the toe of the dune, down into the trough, up over a sandbar, and then down into deeper water. And we're interested in the beach slopes. So the foreshore slope is in this area highlighted in the box. And notice that there's fairly different foreshore slopes for these three storms, where the Matthew foreshore slope is pretty steep. The Jose and Maria foreshore slope, as I pointed out before, is pretty gentle. We're also interested in these sandbars because we think the sandbars could be affecting the hydrodynamics. So I've defined a bar slope, what I call, which is shown for Joaquin by the dashed blue line. And it goes from basically the mean, where the mean water level intersects the profile, to the crest of the sandbar. So it's accounting for how far offshore the sandbar is and how high the sandbar is. So we want to look at the parameterizations for the 2% run-up. There are quite a few parameterizations out there. They all tend to take the same form, where there's this mean run-up component and then two components of the swash, the infragravity and sea swell swash. And I'm going to compare the observations from the Lidar, in particular with the parameterization that was developed primarily using observations from this same location. They had about 400 hours of run-up, or 400 studies with run-up at this location, but it was all during calm to moderate, sort of mostly moderate wave conditions. So they didn't have these extreme conditions we have here, and I want to see how well it works. So first I'm going to look at the infragravity swash. That's what's shown here. The observations are on the vertical. The typical parameterization that's used is on the horizontal. In this case, it depends upon the offshore wave conditions alone, the wave height times the wave length, so that's H naught times L naught. The black line is actually the parameterization, including the slope and the other terms in the parameterization. The black symbols are the small waves, green symbols are moderate waves, red symbols are big waves. I note that all of those fall pretty well along that parameterization line. Actually, if I get a best fit line just to the data, I get the exact same slope as for the parameterization. So this parameterization developed in 2006 with old data for moderate wave conditions seems to work pretty well, and the small, moderate, and big waves all fall along the same line. So we like that one. Looking at the sea swell swash, it's not quite as good. So again, observations on the vertical, parameterization on the horizontal, in this case depends upon the foreshore slope and the offshore wave conditions. And in this case, you see that the small waves, the black symbols, fall to the left of the line. The big waves, the red symbols, fall to the right of the line. So actually, I didn't even put a squared correlation up there because it's 0. Not very good agreement. Well, there are also quite a few theories for the sea swell swash, and they tend to depend on the concept that the sea swell waves in the surf zone are depth limited. And by that, what I mean is, if you're at about a meter of water depth that's sort of mid or upper thigh for me, you can't put a 5-meter high wave in there. It's just not going to fit. It can't go up and down. The bed will go dry. And in practice, actually, in about a meter of water, all you can fit is about a 50-centimeter high wave. So that's why we call it depth limited, because the waves really just respond to the local water depth. You can't fit those big waves in. So those big 5-meter waves are coming towards shore. They're breaking, they're dissipating, they're losing energy. At the base of the foreshore, sort of right before the waves break and become swash, the water might be about 50 centimeters deep. So you can only fit a small wave in there. It doesn't matter how big the waves were offshore. Based on those theories, they suggest that the swash, the sea swell swash, should be independent of the offshore wave heights and should just depend on the foreshore slope and the offshore wave length. So that's what I've shown here, that parameterization based on that. Again, the observations on the vertical, this parameterization now that doesn't have the offshore wave heights in it on the horizontal, and you can see really good agreement. The squared correlation on the right is about 0.8, so pretty good agreement between the observations and this new parameterization. So last we have the mean run-up. That's what I've shown here. Again, observations on the vertical, the parameterization on the horizontal, which again depends on the foreshore slope and the offshore wave conditions. And in this case, notice that all the points fall to the left of the line. So that's saying the observed mean run-up that we measured with the Lidar is bigger than the parameterization in all cases. You don't really see a wave height dependence to that, but when I looked at this data more closely, I did see an experiment dependence. It was different for each storm. And so I thought, okay, maybe that has something to do with this bathymetry in the surf zone, the sand levels and the sandbar location in the surf zone. So I looked at what I called the bar slope there, shown the little inset at the top, and I replaced the foreshore slope with the bar slope. And there's much better agreement. The squared correlation goes from about 0.15 up to about 0.7. And again, no wave height dependence. So the bar does seem to be affecting the mean run-up. That's actually pretty consistent with some prior studies. What happens with the setup is that if the waves break in shallower water, they create more setup. You can think of that same thing with the wind. If the wind blows across a shallow lake, it piles more water up against the shoreline than if it blows across a really, really deep lake. It doesn't have as much effect on the water column. Same thing with the waves. So the sandbar elevation, the sandbar location can have a big effect. So that's what we've accounted for here. So pulling those three together, shown here now, the mean run-up is on the left. That depends upon the foreshore slope and the offshore wave, the bar slope and the offshore wave conditions. The sea swell swash in the middle just depends upon the foreshore slope. It's independent of the offshore wave conditions, sorry. And then the infragravity run-up on the right, which only depends on the offshore wave conditions. Notice also that the magnitude of each one of these terms is about the same. You can't just neglect one of these terms. There's some studies where they assume that the infragravity swash is going to dominate because the sea swell waves dissipate towards the shore. In this case, the sea swell swash is just as big as the infragravity swash. However, if you look at the parameterization, if you go back to that, that's shown on the top of the page here, the swash is fluctuating about the mean run-up. So the swash is going above the mean run-up and below the mean run-up. So when you're actually looking at the 2% water level, you only account for that upper part of the swash. So it has a 1/2 in front of it. What's shown down below is this total summed up parameterization that's given up above now. The observations are on the vertical, the total parameterizations on the horizontal, and you can see reasonably good agreement. There's some scatter about it, but it's getting what's going on reasonably well. So what I want to do, or what I'm going to do, is use that parameterization apply it over for the actual conditions over the bathymetry, the sand levels that were measured after the storm, to see whether or not that will explain the alongshore variability and where the erosion occurred. So that's what I've shown here. The upper panel, again, is that aerial view I showed before, looking down on the beach with the colored bars showing where the dune erosion was maximum. Down below on the vertical, I show the parameterization for the 2% run-up, that's including the surge. The horizontal axis is a longshore distance that's lined up with the aerial photo. So the pier's in the same location in both panels. And the different color curves represent the different storms. So blue again is Joaquin, green is Matthew, pink is Maria, gray is Jose. If you look at the blue curve, notice that there's a little bit of a peak in the 2% run-up. That's right at the southern end of where the dune erosion was maximum, as shown by the blue bar in the upper panel. But the dune toe and all along the beach is roughly about 4 meters. There is a longshore variability in it, but it's roughly on the order of 4 meters. So I drew a horizontal black line at that 4-meter elevation. And if you look at where the blue curve exceeds the 4-meter line, that's lined up pretty well with where the dune erosion occurred. If you look at the green curve for Hurricane Matthew, its 2% run-up is a little bit further to the, or maximum is a little bit further to the south. And again, where that curve exceeds the 4-meter line is roughly lined up with where the dune erosion occurred. And during Hurricane Maria, again, peak is further south. Where it's above the 4-meter line is roughly lined up with where the dune erosion occurred. So it seems like this 2% run-up parameterization or the 2% run-up is related to the dune erosion, is correlated with the dune erosion. Hurricane Jose is also on there in gray. There was no dune erosion during Hurricane Jose. Part of that's because it was at a lower tide stage than the other storms. It does exceed the 4-meter line. There was no dune erosion. This isn't perfect, but it at least seems to be getting the trends right of where the dune erosion did occur. So if we look more at that parameterization that I developed, on the right-hand side, if you look at the term on the right for the infragravity swash, that only depends upon the offshore wave conditions. And we assumed those were alongshore uniform over this stretch of beach. So it's not contributing to this alongshore variability in the erosion or the 2% run-up at all. If you look at the middle term, the sea swell swash, it depends upon the foreshore slope. That does vary along the beach, so it is contributing to some of the alongshore variability in the 2% run-up. However, it's got that 1/2 out in front of it, so that term is about half as big as the mean run-up term. So the mean run-up term, which depends upon that sandbar location, is really dominating the alongshore variability that you see here. So, and that's also something that people have suggested before, but it hasn't been shown as well. The dune toe elevation has been called into, it's something it's easier to measure than the surf zone bathymetry. So people often assume the dune toe elevation is dominant. So in summary, we first did a comparison of the Lidar with the pressure data just to make sure that it could measure the hydrodynamics very close to shore, and showed that the Lidar and pressure-based setup and also the wave heights were similar within a few centimeters of difference. And all those terms I showed had basically a 1 to 2 meter range. So a few centimeters is not the end of the world. We think the Lidar will work for this did work for this study. Using the Lidar data, we were able to show that the 2% run-up level seems to depend upon the surf zone sand levels, and that also that the dune erosion is related to the 2% run-up alongshore variability. We also showed that the sea swell swash seemed to be independent of the offshore wave conditions and only depend upon the foreshore slope. And that's something that I want to look at more in the future. Why did that previous parameterization seem to think that, or show that it did depend on the offshore wave conditions? One possible reason is that they were looking at moderate waves, and that the moderate wave behavior is different from the behavior of these waves during these really big storms. So there is some ongoing work. As I mentioned before, we are doing some ongoing work testing the Lidar system and seeing exactly how the different types of Lidars work. Also developing them for different situations, like possibly being able to look at the foam on those breaking waves. We also are we're still doing some work with the physics, the relation of the dune erosion. In particular, we want to incorporate that dune toe elevation into the parameterization. It wasn't well correlated with the locations of dune erosion, but it does still have an effect, and it does vary alongshore. So it might, hopefully, make that agreement even better if we include the dune toe elevation in there. We also actually did have 2 Lidars operating during Hurricane Matthew. We just finished processing the data from the further north Lidar. So I want to look and see whether or not the alongshore variability in the Lidar measurements is consistent with that parameterization that I made. And finally, looking at that sea swell swash dependence on the foreshore slope. It agrees with theory. It doesn't agree with some of the prior observations. It's something we're looking into further. Thank you.
Do we have any questions?
Thanks, Britt. Nice talking. Question, you might have mentioned this, but I might have missed it. Does the duration of the storms have any impact on the amount of erosion that you might see?
Presumably, certainly yes. If there are a couple of, so those parameterizations that the change in volume is proportional to the difference between 2% level and a dune toe elevation also have a time factor in them. So the longer that the waves are impacting the dune, the more erosion you're going to get. So definitely.
Did you notice any differences in the storms that occurred, like the one that you looked at in particular? Did either of them last longer?
Joaquin did last longer. So the one that had the most dune erosion did last longer than the others. There actually was a nor'easter before Joaquin, and then Joaquin came through. It went by pretty far offshore. So it generated big waves for a fairly long time. That did have the most erosion. Jose was definitely the shortest of the storms. It came by pretty quickly. It didn't have any dune erosion. So I wasn't in this case looking so much at the magnitude of the erosion, more that alongshore variability. But you're right, the magnitude is almost certainly going to depend on the duration of the storm for 2 reasons. One, because a longer storm that impacts the dune for longer is going to have an effect. It's also more likely to end up occurring big waves at high tide, which is really important for whether they impact the dune at all.
Okay, thank you.
Britt, I have 2 questions. One was for the parameterization using the bar. Where or when was that bathymetry collected, prior or after the storms? It might be different,
Yeah.
right?
It's definitely different. And that was bathymetry. I used bathymetry following the storm. And part of the reasoning for that was an assumption that there's some feedback between the dune erosion and the surf zone bathymetry, so that the bathymetry after the storm, in a sense, might be in equilibrium with the dune and the hydrodynamics that are occurring, whereas the bathymetry before the storm got altered. We wish we had bathymetry during the storm, but there's no way to get out there and do it. The bathymetry before, that's actually a good idea. I didn't try seeing what would happen if I did use the bathymetry before the storm. It definitely did change. So it may or may not agree well. I haven't looked at that.
Yeah, I mean,
That's an interesting question, yeah.
After
Yeah.
Just curious. The other question I had was, do you have any inclination if the sort of broader scale bathymetry within the surf zone and offshore wave focusing has potential to impact the run up? So looking at how waves propagate over the whole surf zone.
Wave focusing, certainly, I mean, we know wave focusing can impact run up depending on what the conditions are. In these, I have not looked at that. We have done some stuff in other situations, trying to look at how important wave focusing is to run up with these sort of small scale surf zone features. It probably, I mean, there were during Joaquin, when those big holes were out there, they're pretty strong rip currents, which also can create some wave current interaction that might impact the wave focusing and impact the run up. That's something I haven't looked at. We definitely, at places like near La Jolla, California, where there are deep submarine canyons offshore that are much larger scale, or where there's islands or other things offshore, big burrow pits from where they've taken sand for replenishing the beach, there's a very clear effect on the wave focusing on the run-up. I'm just not sure whether or not the scales in this case are big enough to have a big effect, but something else that should be looked at. Agreed.
Thank you.
Britt, have there been any longer term studies that have looked at alongshore bar variability relative to, vulnerability to dune erosion?
Good question. And
Can I answer?
yeah.
Yeah, I bet there are, but we don't know what they are.
I was trying to think through my head of sort of what.
Because it should be,
You know,
you have pretty convincing evidence to
Right.
suggest that you're onto something.
I think that there probably are. I don't know of a lot of them. And part of it is that there might be some Argus imagery which suggests a bar of a certain shape, but people don't know how high it is. There aren't very many places where there's long-term bathymetry because it's difficult to measure that surf zone sand levels. So the field research facility is one of the few places, and I'm quite sure no one's done it there. And that would be a logical place to do it. I don't know if they have long-term dune erosion data, because until they started using drones for imagery and the Lidar, they were keeping track of the beach bathymetry and the surf zone bathymetry, but not so much the dune. So I'm not sure how much dune measurements they have. Also, prior to about 2000, they weren't getting a lot of the dune erosion there. So that's a really good question.
Can I follow up with that?
Yeah.
So that's a really interesting point you just made, which I'm wondering about. Because in all the years you guys have been working there, and in the experience of the people who've had to pick up the facility, and there's been very little erosion for like 30 years, it feels like. And then all of a sudden you're getting lots of erosion. And it looks like it's coming back, it's creating back again, or something's recovering. Do you have any feel for why? And I realize that a lot of the data that they've collected occurred at times they didn't have any erosion. They really didn't have any way to sort of compare to erosion because they didn't do erosion.
So I can give you Kate Brody's answer to that, which is partly that there was 50 years ago or more, there was a breach way up north towards Kerala. There was a big breach that had occurred. And when they closed that breach, there was a lot of sand put on the beach. And her hypothesis, she doesn't really have data of this, is that there was a big pile of sand that moved south and that kept replenishing that beach. And now that pile of sand is gone and the beach is beginning to erode. Whether or not that's the correct answer, there probably is some sort of large scale variability that was happening. There certainly have been more storms in the most recent years. We didn't have, last couple of years, the last 5-10 years, we've had a hurricane almost every year impacting it, as well as pretty big nor'easters. Back in Sandy Duck, 1997, when we were doing that study there, Steve and I stayed an extra month that we didn't have funding for because we kept waiting for there to be a big storm. We couldn't get any storms. In 94, there were some big storms, but there might have been less frequency of the big storms back there. So there could be other factors as well. I don't have a definite answer. Possibly sand coming down from when they repaired that beach and filled in the beach, helped replenish the beach. But you don't see this big pile of sand with the shoreline being accreted and then it eroding further north and moving down. Actually, it was eroding in Nags Head, part of the south, the whole time. So I think there's probably several different reasons for it, combining.
Britt had those 3 bathymetries, and the third one, she said, "Oh, look, the beach is kind of wider now." They just put a gazillion tons of sand just north of that site 18 months ago, 2 years ago, and that's slowly coming down now and rebuilding the beach. And the wind is blowing it, and it's rebuilding it.
But if you think about that they put that sand, there's a lot of sand from the north part of the property line all the way up to Kerala, basically. So a huge area of beach replenishment with a lot of sand on the beach, building the dune way up, building the beach way up. And that sand's moving through pretty quickly. So it's hard to imagine that they put enough sand on the beach before that it kept the beach stabilized for a period of 30 or 40 years, which is what they basically had, is a pretty stable beach for a really long period of time. So I don't know.
Can I ask one more follow-up about that?
Yeah.
Is there any evidence that additional sandbars are stabilizing the foreshore? You know, I seem to remember that when you had a multiple bar system, the shoreline was a bit more protected.
Yeah, and you know, there's a paper from Nathaniel Plant about, I think it was Nathaniel who wrote that, where he showed basically this series where a bar would break off from the, there'd be a bar in the surf zone, a bar would break off from the shore, they'd move offshore together, the offshore bar would basically dissipate, then there'd be a single bar, another one would break off from the shoreline, and I think that was like a 10 or 15-year cycle. So again, if that's
Not plant.
not plant,
Litman paper.
it's a litmus paper. Oh no! Oh, how embarrassing! It was a really wonderful paper, though. I remember the paper. It was a great paper, seminal paper. Seminal paper, just the wrong author.
That's Nathaniel.
So that was like a 10 to 15-year cycle, right? I got the details right, correct? Hey, anyway, so if that's the case, though, again, you wouldn't expect it to be stable for 15 years. I mean, for 30 years. Sorry, Tom, I will never get that wrong again, I promise you.
Britt, I have a question, a comment and question. I know Tom Litman has a nice system for measuring the bathymetry. You should have him go out during a hurricane.
Hey, that sounds great. Have you heard the Tom stories about Prison Head?
I have a question, or maybe I missed it. Where does the 2% come from and the 2% come from?
It's 2% of the waves or 2% of the water exceed that level.
Why 2%?
So that's actually a really, you know, it's not unusual. You don't want to use the maximum because that can be a spurious data point, basically. So people have used 2% run up for a long period of time. There is some research recently that is suggesting that we probably should be using something like 5 or 10%, that might actually be a more relevant number. But I think it just came out of, you don't want to use the maximum because that's irrelevant. It was something close to the maximum.
It worked for Hillary.
It worked for Hillary.
Yeah, those early parameters that showed nice correlations. Yeah, my guess is Hillary tried 2%.
But you know, I mean, Holman always used 2%. Todd Holland used 2%. There was always this discussion of what's the 2% value, what's the mean value, what's the 98% value. And I don't know where that history came from. And it did work for Hillary.
For all Holman students.
Yeah.
That's true. That's right. Todd, Hillary,
Yeah.
Salinger. Yeah.
All right, well, we'll wrap up there. We thank Britt one more time.